Hey everybody. Today we're talking about independent and dependent events. Basically, two events are independent if knowing whether one occurred doesn't help you guess whether the other one might have occurred. A bit more mathematically, the probability of A given B is equal to the probability of A, and the probability of B given A is the probability of B. By the way, those two things on the sides of the and there are equivalent when neither of the probabilities of A and B are zero. If events are not independent, sometimes we say they're dependent. Another common definition of independence is that A and B are independent if and only if the probability of A and B is just the probability of A times the probability of B. So this is just a simplification of the multiplication rule. Sometimes it gets called the multiplication rule for independent events. Some examples. You should pause, I think, before I show the answers. Try and get the answers yourself. So are these events independent or dependent? Getting diabetes if both of your parents have diabetes, those are dependent events because you're more likely to have a condition like this if your parents have it. Getting a 5 on the first roll of a standard die and a 4 on the second roll. These events are independent because the die has no memory. The outcome of the first roll doesn't have any effect on the outcome of the second. Smoking cigarettes and getting lung cancer. These are dependent because smoking cigarettes increases the probability of getting lung cancer. Notice that here and in many of these other dependent examples, the one doesn't guarantee the other. Some people that smoke cigarettes don't get lung cancer, but it certainly changes the probability. In this case, increases the probability. Two cards are drawn from a standard deck without replacement. The first and the second draws are both aces. So those are going to be dependent because we don't have replacement. So if we draw an ace the first time, it changes the probability of getting an ace on the second draw. Two cards are drawn from a standard deck with replacement. The first and second draws are both aces. So now the events are independent because we've put the card back. So it doesn't matter if we got an ace on the first draw or not. The probability of getting one on the second draw is the same either way. One more example. A manager studies the accuracy of orders in their restaurant, and the results are shown below. We've got breakfast, lunch, and dinner, and we've got whether or not the orders during those times were accurate or not. So I've got a few questions here. The first, find the probability that a randomly selected order from the set was filled correctly. So again, pause. So there are 842 correctly filled orders in this set out of 960 total, so that's 87.7%. Next, let's find the probability that a randomly selected dinner order was filled correctly. So now our sample space is just the dinner column, and there's only 280 possible outcomes there. 249 of those tickets were filled correctly. That's 88.9%. So in this case, the two outcomes, the order being filled correctly and the order being at dinner time, are not independent because the probability of an order being correct, 88.9%, is not the same as the probability of the order being correct among just dinner orders, which was 87.7%. One comment about this. This last example, we were talking about independence from the perspective of classical probability. We were randomly selecting from the 960 orders in that study, and we determined that the two events we were looking at were not independent in that situation. Now, the empirical question of whether future observations of these variables will be independent is a lot more difficult, since our sample data is unlikely to exactly reflect the true population, the population of all possible orders at this place. We're just going to have some random variation.